Ladies and gentlemen, please welcome to the stage from Virginia Tech, Nathan King.
Hello. So I'm going to talk a little bit today about what we call reality computing for resource limitation, which is a kind of a new research trajectory within the Center for Design Research at Virginia Tech in collaboration with Mass Design and Autodesk. So one problem we have in the university setting is that our research tends to stay in the university setting and never go outside. Take, for example, the solar decathlon project shown here. What we've been able to do by collaborating with practice and industry is to start to apply this technologies developed in the university for actual use in design practice. This project shows a performance-optimized facade created through a robotic fabrication process that can be used to control daylighting, views, privacy, and so on. So in the solar decathlon example, it's about a 50-foot facade system that has massive amounts of programmatic variation throughout. But in real practice, we have to deal with cost of labor, expenses for technology, and so on. And so actually applying these outside the university context becomes an issue. Then we move into kind of a problem-driven approach that links our connection with practice, in this case, Mass Design Group and the Cholera Treatment Center in Port-au-Prince, Haiti. So 2010 earthquake, we see an outbreak of cholera. By 2012, 600,000 cases and 7,600 deaths. Kind of represents a systemic issue that started in Port-au-Prince around 70 years ago, dealing with kind of infrastructural limitations, overpopulation, and deforestation. So the question here is, how do we apply design technology, computational design, digital fabrication, kind of reality capture to settings like this? So in the Cholera Treatment Center, we have a complex building that needs to actually serve as a water treatment center. It needs to collect rainwater for cleaning, it needs to provide dignity for patients. And in a way, it's a pavilion structure that has a program to treat cholera, and which is a totally undignified disease to undergo. So within this context, we have a building designed to develop a solution for a cholera epidemic that is a systemic issue, not just a problem that a single building can solve. So on one hand, we could introduce infrastructure throughout the city, develop wastewater, sanitation, and so on, which is kind of the typical approach if we had kind of decades and decades of urban planning, resources, and so on. But from a single building, how do we take this idea and expand it into the entire city, or at least areas that are most impacted by this cholera epidemic, which now has subsided? So we have image here focusing on Cité Ladue, that is the city of God and kind of an emerging informal settlement that changes over time. So on one hand, we have this building, performance-optimized facade, robotic fabrication technologies, and all these questions kind of jumbling around. And then we have issues like informal settlement in Port-au-Prince, totally lacking infrastructure that emerged over the last 70 years or so as deforestation led to water runoff, erosion, sediment coming into the reef, and largely a lot of waste because of lack of sanitation infrastructure within Port-au-Prince. So here we have drone footage combined with an animation showing the kind of trajectory starting about 1920 when the canals were built into the ocean on the coast. And we start with a beachfront property on Harry Truman Boulevard, ending with this site for an informal settlement, which starts to cause problems in terms of design. And how do we design for this settlement from a distributed healthcare system or perspective? So we have an issue of density mapping and understanding how many people are in the catchment area of certain distributed healthcare systems. So the goal of the work is essentially to look at this systemic issue from a city perspective, using technology as a way of mapping, identifying sources and sites for distributed healthcare, and then applying it to informal settlements, which are drastically changing. So we start out with a process of kind of going door to door, finding out, looking at density, counting number of people per square meter, evaluating that based on a distributed healthcare model here, where we have nodes, hubs that are serving as wastewater treatment centers, clinics, and so on. But ultimately driving us back to this question, how do we actually do this appropriately? And this is the beginning of research that the system is needed, and we have this opportunity to look at reality capture as a way to analyze density through, in this case, drone mapping and linking it with computational modeling. So in the kind of extreme resource limited setting, we want to begin to apply these technologies in a way that can start to influence the development of healthcare, education, and so on within cities like Port-au-Prince and other settings in which mass design works. So this, just an introduction to this solution to color epidemic in the color treatment center that we worked on, and then the link that we find in terms of identifying opportunities within these resource limited settings to then apply technology. So it's just a precursor to another project that I'll show, and that it starts with the need for a school. This is Africa Wildlife Federation School in Elima, Congo. One of the, again, extreme remoteness here is causing the resource limitation, not lack of infrastructure. Remoteness results in lack of infrastructure here. All the materials for this building had to be harvested locally. So we have workers cutting down trees, making bricks, all from local materials. This is all something that is required because of the site and the resource limitation of that site. So all materials have to be local. So again, it introduces a problem and really this question: how do we apply technology, computational design technology, whether it's capture, computing, or the fabrication, to these settings where ultimately we need design the most? So here, a totally manual process of cutting down trees to build beams and so on leads us to an opportunity, and that's to answer this research question through technology development. This is a project in Boston, so we go from Elima, Congo to Boston, and a site for the Design Boston Biennial, which is a kind of a festival happens every 2 years in Boston now, and it's kind of third instantiation, and the opportunity to develop a pavilion. So we have the pavilion structure on one hand and the Elima project on the other, and we have this opportunity to start to answer this question: how can we use computational design and fabrication technologies to influence construction in resource-limited settings? Looking at structural analysis through centerline, deflection modeling, here using various computational design tools to analyze structure, which is something typical in practice, but something we totally have no access to in sites that we work, such as the Congo or Port-au-Prince. Developing assembly strategies that can be modeled computationally, communicating complex building systems for application in these settings. In this case, we have the question from the Congo saying, how can we build structures with short span members? Rather than cutting down large trees, how do we make systems that can utilize short span structural members for long span structures? So in this case, a grid shell typology is the research kind of project. We have questions of assembly. So going from the computational model, which in this case was an extreme, shows extreme variation in geometry, not necessarily required for the program, but from a research position and methodology, we want to kind of test the system. So it forces a way to communicate building system for on-site fabrication that is ultimately custom because of the geometric complexity. So we have this identifying mark that shows positions of nodes, struts on a given building or the given system. In this case, we have the left node, the steel part of the building is 205-3, so that's part 205, flange number 3. This strut is part number 325, and it's 10.587 inches long. So I heard someone speaking earlier about tolerances in the 1 millimeter range for the Sagrada Familia. That's not what we work in. We work in multiple inches of tolerances, but in this case, identifying to the third decimal the kind of length of struts. So using fusion to model the assembly of the structure, again, prototypical structure, and then also animation through the fusion platform to communicate the kind of order of operations on site in terms of construction. So again, we're talking about a prototype that's happening as a collaboration within an academic environment with the goal of eventually applying this to structures in resource-limited setting. Back to the resource-limited setting, although this is in Virginia, we have a small bandsaw mill working with local fabricators to create the wood, developing the prototype. So again, an aspect of the work is to actually apply the technology in some kind of fashion that allows us to demonstrate the potential. Developing robotic fabrication technique, which is again a trade-off between what we can do on site and what can we do in the lab. So we have opportunity to hang different research on each aspect of the program. So we want to advance technology on one hand and develop usable systems for these settings on the other. So at the end, the computation is what links it. So we developed this is a dynamo to robot tool that was developed as part of the research to link from the computational design model to industrial robot to allow the fabrication through robotics. So we're still working with kind of advanced fabrication that doesn't have a place in Ilima, Congo, but working with techniques that'll translate kind of building information into site-based construction in some kind of usable manner. Here we're teaching students how to weld, working on the node fabrication, and then a robotic work cell that's inherently collaborative in that the robot positions a node for welding. The student welders weld the fins at each place. And for the Boston project, the pavilion structure, we have around 176 of these nodes, each with 4 different flanges. So the robotic welding process is assisted by the robot in terms of positioning. It's not to say that this is translatable to the resource-limited settings, but the strategy of demonstrating building information on the component itself to allow for site assembly does seem to translate. Translating for the craft-based process of making the wood struts, and then ultimately fabricating it in the shop, this pavilion that is now installed in the Boston Greenway. So from this research, we're starting to look at, again, a grid shell typology, which is something that is common, but in settings that we work in, we're not able to actually use these structures because we don't have a way to analyze, we don't have a way to link to cloud computing due to low bandwidth, and we don't necessarily have access to a lot of skilled labor to create the components needed. But by looking at this kind of advanced technology through the lens of resource limitation and kind of locally fabricated components, we can start to address the application of technology within this built environment for these particular settings. So this kind of leads to this opportunity where we have a project that hangs a lot, from which we hang a lot of research questions. So we have on one hand the context of Ilima, Congo, and how to create long span structures with short span members. We have technology development, so developing the software needed to create robotically fabricated components in some kind of low-cost way, automated fashion, moving directly from the design software into the fabrication environment. And then we have the potential to engage in evaluating that, like how well does the system actually work? And that's where we had the opportunity to build a second version of the pavilion for more of a display purposes at Autodesk University, and now is displayed here. But that allowed us the opportunity to work on the kind of evaluation component. So once the system is built, how do we evaluate it? This shows a 3D scan that was created by folks at a neighboring booth, allowing us to then do a deflection analysis to understand where our deflected shape that was simulated in the software, how that actually responds in the real world. And this is intentionally designed to make everyone nauseated, so I apologize for this rendering. But we can see through this walkthrough that there's massive difference between the actual built shape and the as-built analysis. So we have here about 18 inches of variation from the design model through construction to the real deflected shape. And part of that's that we don't work in millimeter tolerances. We work in, more or less whatever the dimension of your thumb is. That's close enough in the environment, in the kind of the space that we're working in. But in this setting, it allows us to say we have this proposal that says we can take the computational model, we can simulate it precisely, then we can output to a robotic fabrication process that is more or less zero tolerance, and then arrive at the kind of as-built shape matching the computational geometry. In reality, that's not true. We actually have variation that's shown through the scan. So this shows the deflected shape, the design model, which is the green. There's a center line model, which is the deflected shape, which you can barely see in the image. It's more or less the same as the design model. And then the final as-built point cloud, which is the wooden structure, or the brown component of the image. So we see this variation through the as-built model. So by going from computational design to actual construction and prototyping, we start to evaluate these technologies. And so the question for us is, how do we take these technologies, be it capturing through drone scanning, distribution model for distributed healthcare, catchment areas, and so on, all the way down to the building component, and how do we evaluate the building component for use in resource-limited settings through some kind of reality computing platform. So what we hope to do is link these things together and then look at the kind of relationship between the low-tech, the high-tech, and then start to deploy these technologies. So part of being here at REAL is to try to link with people that are actually doing this in practice to allow us a way to kind of collaborate on the development of this for areas that are where computational design technologies are much needed. In this case, we have the Alima Comigo project and Port-au-Prince, Haiti. And if you want to stop by, we have this prototype assembled in the booth next door. And that's what I've got.